Okay, welcome everyone. Welcome to join our first seminar of our online seminar series of the year 2023. And we will follow the tradition to have the seminar on every fourth Friday, 1 p.m. Eastern time. That's going to be noon Central Time, 10 a.m. the Pacific time of every month. Right. So book your calendar, bring your lunch, bring your brunch, and to enjoy the seminar. So today it's our great pleasure to have Dr. Hrayer Aprahamian to speak our seminar. Dr. Hrayer Aprahamian is assistant professor at the Department of Industrial and System Engineering at the Texas A&M University. He received a PhD in Industrial and System Engineering at Virginia Tech. Dr. Aprahamian's research has been focused on interaction between combinatorics, discrete and continuous optimization, and applications particularly related to healthcare systems and the public policy decision-making. And he has been publishing on top journals in our field. His work has been recognized by numerous awards, including finalist for JFIC paper competition, ISE Transaction Awards, Pritzker Doctoral Dissertation Award, among the others. Right? And in particular, he was awarded the 2022 PS Scholar Paper Award, Best Paper Award. And that's why we invite him here today to speak with us and about his award-winning paper on the optimization framework for mass screening strategies. And without further ado, welcome Hrayer, and the floor is yours.
Thank you very much, Chuchi, for a nice introduction. And thank you, everyone, for joining today's seminar. It's really an honor to be able to present my work on this platform. Yes, today I'm going to be talking about a work that I've been conducting with one of my PhD students. So the title of today's talk is an optimization framework for customized targeted screening of non-uniform populations under the availability of multiple schemes and tests. First, let's go over an outline. I'm going to first introduce and motivate the problem. And then I'm going to briefly go over the literature review and the available work. I'm going to go over the research objectives, provide and discuss the decision problem, present the optimization model, and then we're going to conduct a case study on COVID-19, specifically in the United States. Finally, I'm going to conclude the talk and discuss future research directions. If at any time you have any questions, please feel free to interrupt and ask questions in the chat. I'll try to keep an eye on the chat and the Q&A to the best of my abilities. So mass screening is a very valuable and important tool that is used in a variety of settings. For example, it is heavily used to ensure a steady and safe supply of blood for transfusion that are free of transmission-transmittable infections. It's also used, for example, to screen for sexually transmitted diseases, such as in the Infertility Prevention Project. And recently, it has gained significant attention because of its relevance to mitigating the spread of infectious disease outbreaks. And the objective of mass screening strategies is to accurately classify individuals as positive or negative for a given binary characteristics. In our case, we're mainly focusing on whether the subject is infected or not infected with a given disease. So a well-designed screening strategy can provide substantial benefits. And the most straightforward approach is to individually screen every single person. However, in practice, this is not that practical because testing capacity is often severely limited. For example, if we look at COVID-19 data and we track the number of available tests, we can see that even after 6 months from when the first COVID case was detected in the US, the testing capacity was less than 14%. That means that the available tests can only test less than 14% of the population. So because of that, individual screening alone might not be sufficient, as it might not be able to test the entire population or to give a fair or an accurate classification of the population. There are also other challenges that take this problem. One of them is that different subpopulations can have different risk scores. So different subpopulations can have different risk scores. So for example, if we look at data from the Centers for Disease Control and Prevention, we can see that different geographic regions in the United States can have significantly different risk or probability of positivity. And we want to somehow capture this valuable information. In addition to this, we also have multiple competing assays to use. And these assays can be based on different technologies, and they have varying levels of costs and accuracy. And on top of that, we also have different types of testing schemes to adopt. One example is the individual testing that I described earlier, but this is not the only type of testing scheme. So in terms of the existing literature, the vast majority primarily focus on assuming homogeneous populations. That is, every single person is identical to each other. However, as we saw on the previous slide, data suggests otherwise. And because of this, more recent papers have started considering heterogeneous populations. However, existing work on this matter still impose a single assay and a single testing scheme, which is quite restrictive. More importantly, existing efforts have been mainly focused on reactive strategies. Those are strategies, for example, where subjects are prioritized based on whether they are experiencing symptoms or not. And reactive, although valuable, reactive strategies have a number of drawbacks. For example, they fail to provide early detection. And other examples include that it fails to detect pre-symptomatic cases or asymptomatic cases. And in fact, this is quite relevant for COVID-19 because numerous data sources suggest that 35% of all COVID-19 transmissions are due to pre-symptomatic cases, and roughly 30% of all COVID-19 cases are asymptomatic. So it's important to come up with an effective mechanism to also be able to capture or detect such cases as well. Because of the disadvantages or the drawbacks of reactive strategies, more recently, studies have started shifting towards proactive strategies. And in proactive strategies, we target subpopulations to test. However, existing studies on this matter still have some limitations. For example, they impose the assumption of homogeneous populations. They assume testing assays are perfect, and they only consider a single testing scheme or testing assay, and they often do not establish an optimization-based. So the objective of this work is to establish a mass screening model that identifies which subpopulations to target for screening, hence why it's proactive. It incorporates multiple competing assays. It considers different testing schemes, and it also sheds light on the structure of optimal mass screening policies, which is important to us because we want to inform higher level decision making, provide policymakers with guidelines, data-driven guidelines of how to effectively mitigate the spread of disease. And the goal is to identify a strategy, a screening strategy, which is defined by an allocation of budget, assays, and testing schemes across heterogeneous subpopulations. And we want to achieve this in a way that optimizes the overall performance. And in our case, what performance is, we measure through the number of misclassifications. Again, we want an accurate testing strategy. So we count the number of misclassification of testing strategy. And of course, this all has to be done under a limited budget availability because we have limited resources. Now, to best illustrate the decision problem, let's consider a very simple example. In this example, this large rectangle over here represents my entire population, and this population is decomposed in this particular case into 5 subpopulations. And each of these subpopulations has a different risk score based on available data. And in this example, we have 2 testing schemes, which we labeled TS1 and TS2, and 3 available assays labeled A1, A2, A3. One of the first decisions that we want to make is to determine what proportion of each of these subpopulations we want to target for testing. For example, this subpopulation in the top left, 55% of this population would be targeted, and then so on and so forth for the remaining subpopulation. In addition to that, we also want to determine what combination of testing schemes and assays we should deploy across these subpopulations. So, for example, the subpopulation in the top left is going to utilize assay A3 using testing scheme 1. And the idea over here is to figure out the optimal allocation of these assays and schemes and the optimal proportion of each subpopulation to test. And you can only imagine the large number of combinations that are possible, especially for a large number of subpopulations, as we consider in the case. In terms of testing schemes, the literature provides a large variety of possibilities. In this work, we focus our analysis on two of the simplest ones. First is individual testing, which I described earlier. It's as simple as it gets. in this example over here, we have 7 subjects, and we have 2 tests. Essentially what happens over here, we would select the riskiest of these 2, and then we would individually test them. The disadvantage of individual testing is that a large portion of the population is untested. And again, some of which can be positive, which can have detrimental effects later on. To combat this, there's another testing scheme that we consider. It's known as Dorfman group testing. And group testing has been used quite extensively in a variety of settings. And the concept is quite simple. Instead of using a single test to test a single person, what we would do is we would combine the samples of multiple people or multiple subjects into a single subject, and then test that master sample. So in this example over here, we have the same 7 individuals, but we split them into 2 groups. So the group on the left and the group on the right. Notice that if the outcome of the group is negative, such as the one on the right, then testing stops and we classify all members of that group as negative. On the other hand, if the group test outcome was positive, which indicates that at least one of the members is positive, what we do is we perform another tier of tests, of individual tests, to identify the positive members. And as you can imagine, group testing, the simple concept, can greatly expand the screening efforts, even under low budget levels. And this is especially true when we have low prevalence. However, a drawback is that Dorfman group testing may provide less accurate results when compared to individual testing. However, we can negate that in a number of ways. For example, we can play around with the group size. And in fact, a key decision over here, whenever we do group testing, is to determine what is the optimal group size. And that optimal group size need not be the same for different subpopulations. Again, we want to customize based on the characteristics of the subpopulation. So in terms of testing schemes, we incorporate in our framework both testing schemes, individual testing and Dorfman group testing, to be used simultaneously together. For example, a subset of my population would be tested, while another subset would be tested individually, and then the remaining would be tested via group testing. And as I said before, they don't need to share a common group size. In terms of testing assays, in practice, we have the availability of multiple competing assays. And as I mentioned earlier, these are, for example, based on different technologies, such as the PCR versus the antigen test. And what's interesting is that they have varying levels of cost and accuracy. And the trend that we typically see is that the more expensive it gets, the more accurate it gets. And because we don't have perfect accuracy, then we need to define certain parameters, in particular the sensitivity, which is the true positive probability, and the specificity, which is the true negative probability. And both of these values will be less than 1 because the tests are imperfect. And because of that fact, misclassifications are possible. In particular, we have 2 types of misclassifications that we're interested in. False negatives, which are positive individuals that are falsely classified as negative, and false positives, which are negative individuals that are falsely classified as positive. Now, the incorporation of both testing assays and testing scheme is especially interesting within a context that includes population heterogeneity, because we can truly customize based on the needs of the population. For example, expensive tests can be used for group testing in order to mitigate any loss in accuracy based due to group testing, while more affordable, still accurate tests can be used on an individual basis. And that's what we want to capture over here, is to be able to truly customize based on the needs of each of the subpopulations. Any questions so far? So before I go into the optimization model, I do want to go over a brief set of notation. So in terms of parameter, cursive M would represent my set of subpopulations. For example, in the previous example, we had 5, and capital M represents the general setting where we have capital M subpopulations. Rm is going to represent the risk of subjects in subpopulation M, and this risk is essentially a probability of positivity. If we randomly draw a person from this subpopulation, what's the probability of them being infected with this disease? Psi is going to be a set of available testing assays. In our previous example, we had three possibilities. So psi would, the cardinality of psi would be 3, and hence capital T in the general setting. SET and SPT would respectively denote the sensitivity of test T and the specificity of test T. In terms of decision variables, we have three primary decision variables. XMT is the proportion of subpopulation M that is tested individually using test T. YMT is the proportion of subpopulation M that is tested via group testing using test T. And then finally, NMT is the group size of subpopulation M that via group testing using test T. Finally, we are interested in three main random variables. And these are the Fn, which are the number of false negatives, Fp, the random number of false positives, and Tc, that's the total testing cost. And of course, all of these are going to be a function of my decision, which is the testing scheme. So as I mentioned earlier, what we're mainly interested in is finding the most accurate solution or the most accurate testing strategy. And the way we measure that is through the misclassifications. Because of that, we consider minimizing the expected number of false negatives and the expected number of false positives. And we specifically focus on a weighted sum of these two metrics. So the idea over here is that the user can decide which one is more relevant. And we achieve that through this user-defined tunable parameter, lambda. So if lambda, for example, if lambda is equal to 1, then the emphasis is on false negatives. If lambda is equal to 0, then the emphasis is on false positives. And we let the decision maker decide which one is more important to them. But in practice, false negatives typically have much more severe consequences than false positives because these represent positive individuals that have not been detected. For within the context of infectious disease outbreaks, for example, this positive number can lead to the further spreading of the disease. And because of that, lambda is typically greater than 0.5. Of course, we also have limited budget, so that's why we set the expected number of total costs to be within our available budget. And then, of course, the remaining constraint is to make sure that at most 100% of each subpopulation can be targeted. We cannot exceed that. And as a note, capital B over here is the budget on a per person basis. How much is the decision maker willing to spend on a per person on average? Now, of course, the expected number of false negatives, all expressions are heavily dependent on the problem setting. And within our problem setting, what we did is we went in great detail to establish expressions for these. Of course, I'm going to go over I'm going to skip over the details and provide the final optimization model. And I want to note over here that capital A, capital B, and capital A superscript TC and capital B superscript TC are all complicated functions of our problem parameters, but we wrote it this way because it's the most elegant way to present the model. And the key observation over here is that the complexity of this optimization problem primarily arises due to incorporation of the group size. In particular, if we focus on this, for example, on this parameter B subscript MT, we can see that it's a function of the group size over here. This group size leads to polynomial nonlinear terms. And in addition to that nonlinearity, it also imposes discreteness because the group size can only take discrete values. So it somewhat complicates the analysis of this optimization problem. Because of that, our first step was to rewrite this customized testing screening in a more tractable manner. And we achieved that by doing two things. One, we set an upper bound on the group size. And this is actually quite relevant in practice. It's quickly imposed in practice for many reasons. One of them is implementability concerns. It may be very difficult to implement a group size that has hundreds of people. It might be too labor intensive. Another limitation is technological constraints. The testing equipment or machine might not be able to handle such large group sizes. And then finally, and equally importantly, is to avoid the dilution effect. Now, the dilution effect of grouping is a phenomena in which the accuracy of the test deteriorates as the group size increases. And this actually makes sense. Think about it in the following sense. A positive member in the group, the viral load, what the test detects, for example, will be diluted by the negative samples in the group. And clearly, the more you dilute this factor, the harder it is for the test to detect, and hence the accuracy will deteriorate. So we set an upper bound in order to avoid such deteriorations. And in fact, for COVID-19, studies have shown that group sizes up to 15 still lead to favorable test outcomes. But beyond that, we start seeing rapid deterioration in the outcomes. In addition to setting an upper bound on the group size, we also introduced new decision variables. In particular, we define YMTN to be the proportion of subpopulation M that is tested via the Dorfman testing with group size and using test T. So once we have written this more tractable optimization model, what our objective is to analyze it to establish key structural properties so that we would be able to solve it in an efficient manner. During that process, we did identify quite a number of interesting properties. For example, we noticed that in certain cases, some decision variables are guaranteed to be equal to 0. So essentially think about this as a pre-processing step. Before even solving the optimization model, we can figure out that certain pairs or certain combinations would never be in an optimal solution. In particular, we identify thresholds on the user-defined parameter, lambda, below which certain behavior appears. In particular, lambda, for example, is less than this specified threshold, then we are guaranteed that XMT star is equal to 0. What that means is that subpopulation M would never be tested individually using SAT. Similarly, we identify another threshold given by the following expression over here, and if lambda is below this threshold, then YMTN star is equal to 0. Again, what this indicates is that subpopulation M would never be tested via group testing using test assay and group size. And this is quite important for us because we can actually eliminate all of these possibilities beforehand, which will reduce the scale of the problem and makes it a bit easier to solve. We also construct theoretical upper bounds on the budget. So in some sense, this is a budget value that is the best case scenario. We would test everyone in the population using the best possible combination of testing schemes and testing assays. And we were able to write down in closed form what this upper bound of the budget is. And I would like to note, however, in practice, we are way below that budget value, but it's still nice to have to see how far we are from this ideal situation. On the other end, we identified the budget threshold below which the solution follows an elegant structure. In particular, when we are severely limited on resources, the optimal solution will tend to only target a single subpopulation. Again, when we are extremely limited on resources, and even in that subpopulation, we would not be able to test that entire subpopulation. So what happens in this case is we are able to characterize and quickly obtain what is the optimal subpopulation and what is the optimal proportion to test, and of course to determine what combination of testing assay and testing schemes to use. So at this point, in some sense, we have solutions to two extremes. When the budget is extremely high, that's the theoretical upper limit. And when the budget is relatively low, we are able to solve. And the remaining question is to be able to understand the structure of the solution in between those two budget thresholds. So on our next effort, what we try to do, we try to characterize the optimal solution as a function of this budget. And this result is formally stated in the following theorem. I know it's long, and believe it or not, this is a shortened version of it, but the essence of it is very simple. What we were able to show is that the optimal solution follows a threshold structure based on the budget level. Essentially, what we were able to show is that between these two budget thresholds that I talked about earlier, we can find budget thresholds. In between these budget thresholds, the structure of the optimal solution remains the same. What do I mean by the structure? The subpopulations that I target are the same. The testing schemes and testing assays are the same. Of course, the proportions may vary, but the structure is the same. And that's what we were able to show. And moreover, this theorem allows us to write a very efficient algorithm to do two things. One, to efficiently compute these budget thresholds and to extract the optimal solution rapidly just for a given budget. So if you give me a budget, I can identify the two thresholds that I belong in between, and then I would extract the optimal solution. I can construct the optimal solution. So in summary, this theorem allows us to very efficiently solve the problem, even when we have large problem instances where we have thousands and thousands of subpopulations, as we do in our case. So any questions for now? Okay. So in an effort to demonstrate usefulness of our method, what we did is we conducted a case study on COVID-19 in the United States. In particular, we consider each county as a category, as a subpopulation. So we end up with a total of 3,143 counties and county equivalents in the US. And we estimate the risk based on available COVID data sets. In particular, we mainly use two sources, the Johns Hopkins University, the data sets from Johns Hopkins University and the United States Census Bureau. And what we were able to do is to estimate the risk of each and every county. And of course, several other factors played a role in this, including the factor of underreporting, so on and so forth. And even though I'm not going to discuss it in this talk, we also did resiliency tests. So what if these estimates were wrong? How would the solution behave in those situations? Even though I'm not going to share results regarding it. In terms of the assays, we're going to consider 3 COVID-19 diagnostic assays that I showed earlier. And they have, as I mentioned, they have a range of testing costs and a range of sensitivity and specificity values. And as for the testing schemes, it's going to be individual testing and orphan testing, as I motivated earlier. So we compared the performance of our solution to what we refer to as conventional testing strategies. And in these conventional testing strategies, we do not consider multiple testing assays. They are based on a single testing scheme, and they fail to target subpopulations. And it's important to note that we don't compare to any conventional testing strategy, but rather compare to optimal conventional testing strategies to give them the best fighting chance, basically. And the way we construct these conventional testing strategies is somewhat interesting because we use the exact same platform, CTS, to achieve that. And we believe that we do that in order to have the fairest comparison. And the way we achieve that is by, one, getting our data set and aggregating all subpopulations into a single subpopulation. That way, we are no longer incorporating subpopulations, and hence the model will no longer target subpopulations. And once that is done, we restrict the model to a single assay and a single testing scheme. And since we consider 3 diagnostic tests and 2 testing schemes, we're gonna end up with 6 possible combinations. So we're going to compare our method to these 6 possible conventional strategies. So the results are shown in this figure, where we plot the percentage of misclassification. That is the percentage of the population that is misclassified as a function of the budget. That is, for each budget level, we solve our model, and we also optimize the 6 conventional testing strategies that I talked about earlier. And we plot the percent of the population that is misclassified. And what we can see is that our proposed solution consistently outperforms all of the conventional strategies. In particular, if we look, for example, at the individual testing PCR, which I think is relevant because in many cases, people went ahead and adopted an individual testing PCR strategy. We can see that when the budget is extremely low, our proposed solution and that coincide, which makes sense because if the budget is extremely low, we don't have any budget to test. So the outcome is going to be the same regardless of the testing scheme. On the other extreme, as the budget becomes extremely high, again, we see that the two coincide. And again, this is not surprising because of the budget. If we have enough budget to screen everyone individually using PCR, then great. That is going to lead to the lowest misclassifications. However, what's important is that in between, the difference between the two is huge. In fact, on average, our proposed solution reduces misclassification by an average of 47% over conventional strategies. To do a more thorough comparison of the percent improvement of our solution over conventional schemes, we also plot the percent improvement over conventional screening strategies with the best performing diagnostics. In particular, we look at individual testing, for example, and only select at each budget level the best performing diagnostic test. And we also do that for group testing and then plot the percent improvement. And what's interesting about this plot is that we can see 4 distinct regions of the budget thresholds. In particular, when budget is extremely low, group testing is more favorable out of the conventional schemes, of course. And this behavior alternates until we hit at the highest budget bracket, where individual testing becomes the dominant factor over there in terms of performance. But the key takeaway over here is that by appropriately customizing, we are able to achieve on average around a 50% reduction or improvement in performance. That is a 50% reduction in misclassifications. What we also were interested in is to see the distribution of group testing and individual testing. What is the proportion of tests being conducted via group testing, and what proportion is being individually tested? And the results is very interesting, actually. Again, we do this across different budget levels. When the budget is extremely low, not surprisingly, group testing is going to be the dominant factor over here. Again, group testing expands the screening efforts, so it makes sense to do that. On the other spectrum, when the budget is extremely high, individual testing dominates. Again, this makes sense. Individual testing leads to better classification rates. So when enough budget is available, then that's what the model is going to do. But what's interesting to see is that at the extreme, at the highest budget level, the solution does not converge to a situation when everyone is individually tested, but rather a subset of the population are still tested via group testing, which is somewhat interesting. A more interesting behavior as well is this wave-like behavior of the structure, which at first puzzled us, and then we realized that actually has a very nice intuitive explanation. And it's mainly attributed to the incorporation of different testing assays. So starting with the lowest budget level, again, we use the cheapest test via group testing. As the budget increases, more people will be tested individually using this cheapest test. This will continue to happen until a certain budget level. After this budget level, it becomes affordable to start using the more expensive test, or also more accurate, but using group testing. So that's why the proportion of group testing starts to increase, because more and more people are being tested group testing with this more accurate test. Again, this continues to happen until a point where it becomes affordable to start individually testing subjects based on this more accurate test. And that's why the proportion of individuals starts increasing over here up until that point. And this point is, this is where the PCR, which is the most accurate and the most expensive test, becomes affordable to start using via group testing. That is why group testing starts increasing again, until a point where a PCR becomes affordable to do it in an individual manner. And from there on, it goes, the individual increases and the group testing reduces. So again, we expect if we have more assays, we would experience more of these wave-like behaviors. We were also interested in seeing the composition of the testing assays. So over here, this plots the proportion of each of the assays that are being used. Again, some not surprising observation. When the budget level is extremely low, then we would use the cheapest test. When the budget level is extremely high, we would use the most expensive test. And again, keep in mind that we pre-filtered the test based on certain characteristics. So if there was a test that's more expensive and less accurate, it wouldn't make sense in the first place. Those tests were removed. So over here, the test that we consider more accurate, more expensive is more accurate. And a more interesting observation is that this result indicates that it is never optimal to select to utilize more than 2 assays at a given. Next, what I want to focus on more is the geographic-based data that we have. Keep in mind that we used geographic information based on the different counties, and this allows us to do some interesting analysis from a geographical perspective. So what we were interested in seeing is the distribution of the testing scheme across these regions, across these counties, essentially. So my PhD student diligently created this animation. Keep in mind that each one of them is the optimal solution of our model. And then they were glued essentially together to form this animation. And the way we read this is that counties that are color coded as red are counties that are being individually tested, and counties that are tested via group testing are provided by this are represented by this color scale over here. And this color scale indicates the group size. So there's a lot of information in this animation. Dark blue represents a group size of 2, while I believe this is yellow represents a group size of 12. And the counties that are not tested are represented in gray. And we can see some interesting dynamics over here, which is somewhat consistent with what we saw before. Initially, when budget is 0, no one is tested. As the budget increases, we first have a large proportion of group testing, and then we start seeing this wave-like behavior that is described earlier. group testing increases and then reduces and then increases and then reduces. Then finally, as the budget becomes high enough, we continue to we try to individually test as much as possible up to a certain limit, because certain subpopulations will always be optimal to be tested via group testing. So we thought that this is somewhat interesting to be able to see what sort of testing schemes and testing schemes are being deployed across the country. Moreover, a geographic-based analysis also allows us to have other high-level observations. For example, by utilizing our optimal solution, what is the optimal budget allocation across states? So that's what we did next. We were able to identify the percentage of the budget allocation across states. And again, this can provide policymakers with guidelines of how to optimally distribute budget. Not surprisingly, California and Texas lead to have the highest proportion, not because they are special in any ways, but because they are the two most populous states. However, what's interesting to note is that our results show that depending on the characteristic of the state, this number might not be proportional to its population size. That is, if the state itself is less risky than other states, then the budget allocated would be less than its proportion in terms of population. And similar in the opposite, if a risky state will have a higher budget allocation, higher than its population proportion. So we think that these results are valuable just to give an idea from a federal perspective how to distribute testing kits and how to distribute resources essentially across different heterogeneous geographic regions. Any questions? All right.
I'll ask one actually.
So, please, Laura.
So did you do any comparison where you looked at a strategy in which, okay, within a state you do the optimal scheme, but the total for the state is allocated according to the population size, like almost if you're viewing this as like fair, maybe from a certain perspective, like how much does that affect things?
Yeah, that's a very good question. We did not do that analysis, but that's like a pro rata strategy, right? Where you give each state its fair allocation of budget based on its proportion, and then you would use that in an optimal way. Excellent point. We did not do that comparison. I would suspect we would still observe some meaningful improvements over that. But to add on that, Lauren, once that budget is allocated to a given state, you no longer care about how it's distributed in that state?
Well, I was saying, I mean, I guess you could do either way, just a simple rule within the state, but kind of like centralized control of allocating all the tests to different counties versus like, okay, within the state, they get this fixed budget and then they allocate to the counties, perhaps in that perspective. But yeah, so
yeah, no.
Although I guess you could go down to county level too, and do based on population by each county as well.
Right. So the more we do that, the deeper we dig, clearly the performance is going to deteriorate with that, as expected. However, the advantage of that is fairness. It is fair in terms of geographic distribution. Thank you. Yeah, exactly. Exactly. So that's why an important component that we didn't focus yet on too much is fairness of this. So how do you measure fairness, and what is the price of fairness for adopting this? If the benefits which we are reporting over here are substantial enough, then maybe that can justify having small deviations from what is considered fair. Very good point. Thank you. Other questions? All right.
If I may,
please
try to interrupt. So I guess how you allocate your testing resources also depends on the prevalence of the disease, right? So it depends on is this state or county has a very bad epidemic right now versus other counties. So first of all, I wonder how different prevalence could be in terms of COVID, right? It's a pandemic, everybody get a very bad situation, and how big a variability could be between the counties or between the states. The second is, if, let's say from policymakers' perspective, they want to make an allocation for the budget. This epidemic situation changes every day. So the prevalence may change just like a roller coaster. So how would you do maybe average or aggregated level to inform that?
All right. Thank you. Thank you for your questions. Very good questions. So let's start with the first one regarding the variability. I think that this figure speaks for itself. There's huge
Okay.
in terms of the prevalence across counties, and this is based on real data. We're not making numbers up. This is based on real data, and it truly shows the heterogeneity of the population, which I think makes a stronger case for such work, where we can take advantage of this. So, in terms of your second question, absolutely, this is a very dynamic problem, or the problem setting is very dynamic. And in some sense, we have looked at a snapshot image of what's happening and tried to optimize that. The way we view this is twofold. One is that we can use the snapshot to make the best decision right now, implement that decision, and then re-update our decision maybe on a monthly basis or on a quarterly basis based on a new snapshot. So in that approach, we can use this study as is. We can get the snapshot, make a decision, deploy that decision, and again have a new snapshot and repeat. A more interesting way, which is part of the future studies that I'm going to discuss in a bit, is to incorporate this into an epidemiological model, such as a compartmental SIR.
Okay.
Because
that's super cool. Yeah.
That is super cool, but it's super hard.
Yeah.
So right now I'm working with one of my PhD students, actually. You're going to see some of the future works that I'm doing, where we look at not just screening, but vaccine policy and social separation all in tandem within a within a network-based model. Forget compartmental models.
Yes.
It's very interesting. So I'm going to talk about that in a bit later on. But yeah, excellent.
All right. Thanks.
No worries. Any other questions? All right. So to conclude, we study the problem of targeted screening heterogeneous populations under limited testing budget. We construct an optimization model which incorporates different testing schemes and available assays, and we identify an efficient, globally convergent threshold-type solution scheme that characterizes the optimal solution across the entire budget spectrum. And we consider a granular geographic-based COVID-19 case study in the US, which revealed substantial benefit. In terms of future work, we want to incorporate other testing schemes, such as array-based testing or hierarchical group testing. We want to enhance the customizability of the model by allowing different stages of the group testing scheme to utilize different assays. And we want to factor in other subject-specific information beyond probability of infectivity. For example, different populations may have different mortality probabilities. And we want to consider a combination of reactive and proactive screening. Reactive screening is still extremely important. For example, what do you do with people experiencing symptoms, right? You have to test them. So a key question that I'm working right now with one of my PhD students is how much of the budget should I reserve for reacting and how much should I use for proactive? That balance is kind of nice. And finally, as Chuchi asked, we want to embed the formulation within a compartmental model that describes the evolution of the disease, because that's where we truly capture how our decisions are impacting the spread of the disease in the first place. I do want to thank the research team, specifically Jailen, who's my PhD student, and Dr. George Golovko from University of Texas Medical Branch. In fact, this picture of Jai in the top right is right next to the computers at A&M, which he used to solve some of our models. That's pretty cool. This effort is part of this work is part of a much bigger project where we're working with UTMB. And as you can guess, we want to mitigate the spread of infectious diseases through screening. We want to identify optimal testing designs and allocation of limited testing schemes, limited testing kits. And one interesting prospect is that UTMB right now is involved with the West African Center for Emerging Infectious Diseases, which aims to address animal to human disease transmission and the consequences. So the idea over here is that we want to test animals to detect mutations before they transmit to humans. And that's something that we think is cool, where we can use our targeted framework to construct a network of labs prepared to respond quickly and effectively to future outbreaks. And the questions over here, where should we establish the facilities? And what type of animals we should test based on the given risk factors. And UTMB has plenty of data, and this is a project that I'm really looking forward to. A number of papers have appeared because of this work. These are the most recent. This paper is under second round of review with NRL. We have one submitted to IJOC, two under second round with OR, one IJOC as well, submitted to IJOC, and one to be submitted to stochastic systems. Since I have a couple of some time, I want to talk about other projects that I have been involved in. So one is pandemic management. Again, this goes back to the question. So I've been working with my PhD student Sudi in collaboration with TDEM and the TMAG to construct a more complete or more comprehensive pandemic preparedness platform, where we look at screening schemes, vaccine allocation strategies, social separation policies that incorporate not only subject-specific characteristics, but also subject-specific interactions. So the downside of compartmental models is they assume a uniform interaction. So what we do is we approach it from a network perspective, and key question that we're trying to answer is how the social topology impacts decisions, vaccine distribution, so on and so forth. That's something that we're investigating right now. We have a number of papers, one to appear in ISC, two under second round ISC, two under second round MRL, and one under second round with informed journal data science. Another project that I'm extremely excited about is essentially a post-pandemic, one of the post-pandemic consequences, which deals with mental health, particular college mental health. As you can imagine, COVID-19 had a severe impact on the mental health in America in general. 1 in 5 Americans suffer from mental health illness, and college students have been particularly prone to this. And in fact, suicide recently became the second leading cause of death on college campuses, which is, for me, a crazy statistics. It's a scary statistic. So what we're doing is we're collaborating with Texas A&M University's Counseling and Psychological Services and CCMH, which is the College of Collegiate Mental Health, a network of 700 CAP centers, in order to streamline operations, improve access to critical mental health services, and we want to optimize outcome and maximize by constructing the maximally effective treatment plans. I'm collaborating with Dr. Lucen Taimo, our department head and colleague of mine, and 2 PhD students, Soham and Yusuf. Again, I'm very excited about this project. There's a lot of very interesting tools that we're using, including non-stationary queuing theory, simulation optimization, among others, and time series forecasting as well. We have a few papers, one submitted to IJOC, one to appear in simulation, and 2 submitted to one submitted to Journal of American College Health, and one to be submitted to stochastic systems. Finally, I've also been involved in a couple of projects outside of healthcare. I know this is HAS, but I thought that it would be interesting to show that some of the techniques that we develop can also be used in other fields. I've been collaborating with Dr. Dinakar Sagapuram, who's a manufacturing assistant professor in our department, and his student Harshit Chawla, in order to solve a problem that they're having. So the objective over here is to characterize material properties, and they have constructed novel experimental setups, but in order to be able to characterize the material, they end up requiring to solve a nasty nonlinear optimization problem. And it's important for them to get global optimal solutions, which was the key challenge of this problem. So what we did is we worked with them in order to establish a novel spatial branching procedure based on convex relaxation to obtain epsilon optimal solutions. And this is useful for any experimental setup and any constitutive model. So those are the benefits of this approach. And we've been collaborating with Sandia National Lab and Los Alamos National Lab. Finally, and some papers from this effort. Finally, this is on the more recent side, I've been collaborating with the data science faculty, Dr. Ray To, in our department, where we want to establish surrogate models for estimating the response of complex large-scale simulations. My role on this is to help construct new simulation optimization procedures to be able to optimize large-scale simulations. Essentially, we look at 2 approaches: stochastic approximation and sample average approximation. And one of the objectives of this effort is to optimize the large-scale simulation that we have built for the mental CAPS project, for the mental health project, and we want to use those tools to optimize that, to come up with optimal schedules. I spoke a lot. I apologize for that. So that concludes my talk, and I'll be happy to take any questions. Thank you.
All right, thank you, Hrayer. This is really interesting talk. Very exciting project, a lot of interesting perspectives. Okay, so for the audience, feel free to just unmute yourself, ask questions, or you can just put questions in the chat box, and then we will discuss that. Yeah, in the meantime, I just have two quick thoughts. One, first, it's not really a question, it's comment. So since you mentioned you work with the center to do the testing among the animals. So actually that reminds me, that could be even go further. It's not only animals, could also be applied to agriculture, to the crops. I had the idea because the other day I was talking to colleagues at Penn State from agricultural engineering. They also study infectious disease model. They study how the insects migrate from one to another. It's like an infectious disease process. So there are a lot of commonalities between, although it sounds like a very different fields, but in the core, the mathematical or the dynamic process, a lot of things in common. That's really interesting. Yeah, since you mentioned animal, that just comes to my mind.
Very interesting thought. Yeah. So what I found is the more I talk with people, the more the more perspective I hear, and this is very interesting. I'll definitely look into this. Because Texas A&M, the A stands for agriculture. So,
that's right. Yeah.
So it makes sense for me to capitalize on such things. So yeah, thank you for that comment.
Yeah. Okay. So the other one thing is a little bit more technical. I'm just curious. So in your model, in your formulation, that becomes a nonlinear optimization problem. So do you end up solving this problem, just throw that to some solver, or you have to develop very ad hoc algorithm, or I don't know, those nonlinear optimization, you have to derive specific optimality conditions to solve them?
We essentially use theorem 1 to construct two algorithms. One algorithm to identify the budget thresholds, and then the other algorithm given a budget to extract a solution based on these results.
Okay.
Okay. So we don't use off-the-shelf optimization solvers. No.
Okay, so you have to derive something ad hoc to the problem structure. Okay.
Exactly. It's all built in.
Okay, interesting. Okay, so any other questions from the audience, from the panel?
Yeah, I'll ask another question. I guess, Chuchi, you were kind of touching on this earlier, but this idea of like the risk estimate for a population. So you're mentioning that you're getting that from like national data, but in turn, where is that national data coming from? I'm kind of wondering, is that in part dependent on the testing scheme you're using? In which case, maybe you have some kind of feedback loop that if you're testing better, you're identifying more cases, you think that the risk is higher in a particular area. So to what extent, do you incorporate that? Or if not, I think you mentioned like, dealing with some robustness to those risk estimates. Just wondering to what extent you think you could handle that, or I'm imagining that presents a whole new set of challenges as well.
Well, thank you very much for the question. And indeed, it does present a whole lot of challenges, but here's my take on it. You're right. Whenever we're using whatever data that we have, including CDC or other sources, that essentially captures of what's happening right now in terms of testing scheme. Regardless of that, it's still a snapshot of what's happening right now. So yes, there is a feedback loop. And that's why when I said that the objective is to incorporate this into a spread model in order to capture that feedback model. Does our testing scheme impact the prevalence, which the prevalence itself is going to impact the testing design, and then back and forth.
Yeah.
So the chicken egg problem. Yeah.
Right.
It is. But the important thing is that all I want at time zero is a snapshot, regardless of what's being implemented. That snapshot is important. Regarding your second point, the accuracy of the risk, it's something that we were very concerned about because there's many factors. What is being reported is not always the only case. There are sometimes the reporting numbers are off. So what we try to do is we try to look at the state level, if possible at the county level, to try to quantify the underreporting. What is the estimates of under, to factor those in and to get a final metric. I do not claim that these final risk metrics are perfect. They're not. That's why a component of our study is, they're not. Let's use them to come up with a strategy, come up with a solution, and then let's test the solution in situations where the risk is completely off. would it continue to outperform other conventional strategies? And what we were able to show is, yes, it continues. It might not be optimal according to this new observed risk values, but still it outperforms other conventional strategies. So that's the way I would respond, at least to that question.
Great.
Yeah, I think it would always be challenged to estimate the real prevalence, no matter what the disease, right? So, yeah, I think I totally agree. I think that's you make decision based on the best information you have, right?
Absolutely.
And acknowledge that information is not the true value, but the best you can get, right? So if there are people, I think maybe some statistician can have their own way to have some additional inference on the prevalence, and then those estimated prevalence can be used to fit into this model to determine the allocation. So I think that could always be done. Yeah,
absolutely. By the way, we're not making the claim that these are the best estimates on the world in the world. Definitely not. I am sure there are much more competent and qualified people to do a much more thorough analysis to get these estimates. All that we wanted is some reasonable estimates of the risk just to be able to use within our firm.
Okay. All right. Do we have any other questions from the audience? Okay. Well, if not, let's thank our speaker again. Thanks for speaking at our seminars, and wish everyone has a great semester, off to a great start. And I hopefully see you guys next month.
Awesome. Thank you very much for the opportunity, and thank you everyone for joining.
All right. Thank you. Take care.